everyone. Today we will talk about lecture 6 of real analysis, which talks about accountability, and then moves on to sequences and series, which is a very important topic to talk about. First part obviously will be the accountability part, and then the next part will just be talking about sequences and series and discussion of limits. We'll actually get to limits in this lecture. And it's a pretty long lecture. Oh no, lecture 7 is, there is a lecture which is pretty long. It's lecture 6 only. Lecture 6 is the pretty long lecture. Lots of notes. So we already talked about the triangular inequality and the vector representation of it, so you can see the last video for YouTube. So we proved this triangular inequality if x, y are in R. We know that this is true. If it works for one number, obviously it could work for two. And same situation over here. Negative x plus negative y. Less than or equal to negative x plus negative y absolute value, or same thing over here. And now what does this imply? This implies, I think I can speak faster than right at this point. Negative x plus negative y So look at this. This makes sense. Negative x squared absolute value of x plus absolute value of y is less than or equal to x plus y, which is less than or equal to absolute value of x plus absolute value of y, which that implies x plus absolute value of x plus y is less than or equal to value of x plus absolute value of y. And how does this work? Well, this and this is anyway, so these two situations both form this over here. These two situations are both less than this, less than or equal to this. This could still equal to this, because less than or equal to and less than or equal to. But in total, this is less than or equal to. And the reverse triangle inequality this is the reverse triangle inequality, just the reverse of a statement. Now here's a question. It's like a question and answer situation. Oh shoot, I forgot to put that box. And the proof box. Q is the rationals are countable. Remember we were talking about. We never talk about R being countable. I mean, like I mentioned R is uncountable. So you already probably know that. Oh, I just told you the answer. Oops. Well, here's it's saying no. Now we'll prove why later. We'll get to like many different statements and talk about decimal representations pretty soon. So it gets very weird from now on to get this decimal representation. So I will try to instead of going through all of these processes by going through decimal representations and weird notation looking, I'll just tell you the idea for why, and we'll prove another statement. So this might actually be pretty short because I'm skipping all the decimal representation nonsense. So it's no, and remember how you take away sets? Well, think about how you take away. So there's the real numbers and irrational numbers. So obviously it's a set of irrational numbers, which is not actually denoted by this. It's just my own thing. I'm going to denote things by myself. This is not official. So I'm happy that this lecture might be a bit short now because of the diagonal representation. Decimal representation might be a bit weird. That's the irrationals. Irrationals are uncountable. So this is how they would do it. They would do dk 10k dk minus 1 10k minus 1, but in my opinion it's a bit weird. This is weird. So I actually have all these notes. Oh, by the way, something cool. Oh, fine, I'll put the definition because we all need definitions here. And the theorem. So let x, so we are getting some weird work in. Let x be from 0 to 1, not including 0. This is the interval. And let dj oh god, that was a horrible DJ. So now this is DJ. It's basically 0 to 9. Its digits are 0 to 9. We say x is represented by the digits d minus j. J is in naturals, or in this situation, since it's 0.0 to 1, it's represented by these digits. Now here's a cool thing. Say so x equals to soup of all the fractions used in the making. So this might make no sense right now, but I'm going to do a different example than what you have here. So this is x, okay? So this, we know this x equals to 25 over 99. And the soup of to 10, 5 to 100. And since this is repeating, we do 2 to 1,000, and 5 to the 10,000 going on. It's basically just like the decimal form. Then the soup equals to 25 over 99. Very interesting. Now I will tell you and here's a star equation which will come up later. X equals to 0.d minus 1. This star equation will be mentioned. It's basically just, again, the decimal representation. But now, this is important. Another theorem relating to Cantor. We're coming back and seeing Cantor in action. This guy did a lot of real analysis stuff. So, now, this is a very important theorem. So all the numbers between 0 to 1, not including 0, we're not including 0, guys, is uncountable. Why does this imply R is uncountable? Well, the cardinality, oh my god, this is impossible. God. Guys, you know what? Since absolute value and cardinality can confuse you, I'm literally gonna just put card. I'm going to put the set in here, so because absolute value things could confuse some people. I just know for a fact that they're mentioning cardinality right now. So now, if we ever get into a cardinality situation, so yeah, basically what you're seeing here is that the cardinality of the set 0 to 1, not including 0, again, so instead of having to put this, at this point you just should know this is what I'm referring to, equal to the cardinality of the real numbers. So this is what implies R is uncountable. And so here's the proof. By the way, I'm going to mention the theorem which I skipped because I just realized it's needed in the proof. So here's the theorem. Number 1, for every set of digits DJ, J is in N, it's impossible to write on this thing. So DJ, J is in N, with D negative J equals to 0. So basically all the one-digit numbers. Then there exists a unique element in 0, 1. There exists a unique X in 0, 1, and again you should know it's just not including 0, such that X equals to 0.d negative 1, d negative 2. So there's always a unique one. Now why is this important? You'll see later. Also, for our purposes, 0.5 equals to 0.49 repeating. Just get used to it at this point. Is there a real number in between them? No. So they're the same thing. Remember, if x is less than y, then by the density of the rationals, we can prove this. In fact, you know what? I'm gonna prove this debate once and for all. 0.9, repeating, equals to 1. How is this possible? Density of the rationals. It's defined. If x, y are real numbers, and let's suppose that and x is less than or equal to y, then there exists a R and Q such that x is less. Oh my god. What? So, say 0.9 really is not the same. So let's assume this. Then there exists a number in between. So what would that number be? How will we find this number? It's 9 repeating and 1. Is there any number in between them? No. There is no number in between them because there's infinite amount of 9s. That's already the biggest you can get. So no. Same thing with this one, and same thing with 0.5 and 0.49 repeating. Same number, okay? You guys probably already knew that anyway. And here's the second part of that theorem. For all x in the set 0, 1, not including 0, there exists a unique digits D, J. Why are we using J? J, N. So we know that, such that star equation x 0 d negative 1 such that star and 0 1 to d n is less than x, which is less than 0.d n to d negative 1 10 to the negative n. Now this makes absolutely no sense, or you might not understand it because I'm getting confused myself. So let's just do this proof. First, we're gonna have to create a very annoying diagram, and then we'll get to the proof. Here's the idea of why it's not true. This is Cantor's diagonalization argument. You might have seen it. Why the reals are uncountable. You said that you might have seen this, but here's the way we're gonna do it. Oh, this is gonna be painful. Please wait. So, of course, this is x of 2. Second number, d negative 1. I'm just gonna do the d. I'll put the top part. Actually, this is more inefficient. So we're creating this graph over here. And you'll see what we're trying to do. So it took some time. It's gonna take some time. But it'll be worth it to show you the argument. It's very Cool idea. Oh yeah, I also forgot to do it on the third row. Then I have to do dot 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 dot. So you know what I'm gonna do? I'm gonna take a screenshot. That was the worst screenshot I've taken. Oh no, that's even worse. No. What? No, that was not meant to be there. Fine, this is much better. So I'll take this one, look at it, and see if it's good. Okay, so I will take the screenshot and delete every. Yep. All this hard work for no reason. Basically, we're just supposed to take the diagonal, so if anything happens, at least now you know. So this won't exist no matter what. This will be a new number. So this is a number which won't exist because, you know, this is the numbers and this is just taking this. So over here it's 1, 2, 3, 4. And now over here we're taking nice diagonal. Can we take the other diagonal as well? I don't know anything about this. But I'm thinking now, why don't we just take, what if we take the other diagonal? Well, that's impossible because, like, it's gonna not, okay. See, this is why I needed the screenshot. The other diagonal is literally impossible. What was I thinking? What? No. No. What the? No. 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 Okay, that was a lot. Finally. So, this is our web. And now we can just choose our diagonal. So this won't be there. So that's the idea, and now we'll get to the proof. It's by contradiction. Suppose the cardinality of 0 to 1 not including 0, or as you should know by now since I wrote in this so many times. And now I'm just literally going to put C. So suppose this. And we're going to prove that this is impossible to hold. Then there exists in x, function x, n to 0 to 1, which is bijective, because we know when the cardinalities are equal, there can exist a bijective function. For each n, we write x to the n equal to 0 dn minus 1 minus 2. So now let e negative j, why is it negative, let out two values. One and 2 if the other condition is the opposite. So 1 if dj negative j is not equal to 1, and 2 if it is. Y equals to this. So y equals to this. Since all ej's, e negative j's are either 1 or 2, they're definitely non-zero, so this is non-zero. This is either 1s or 2s because each 1 or 2. So this implies for all in a natural number, zero E1, E2, En is less than y, which is less than or equal to 0.E1. To E negative N, which then implies y equals to 0.E negative 1, E negative 2 is a unique representation form. Since x is surjective, there exists in M, in N, natural numbers such that y equals to x of M. Thus, d m of negative m equals to e negative m, which doesn't equal to d m negative m, because remember how e was defined? 1 if dm negative 1 isn't 1, and 2 dm negative m equals to 1. Since these are obviously not equal, there's a contradiction, and that's going to be the end of countability, and this is going to be the end of review, and we'll start a review of earlier topics and other stuff, and now we'll start getting into the depth of real analysis of sequences. I'm actually on lecture 9 now, and at this point we're talking about limits and convergent sequences and theorems about them, and special convergent sequences, and we'll get to lim supernums and lim infimums in lecture 9. So, yep, we're going to cover sequences and series in the next lecture, which might just be right after this lecture because I feel like doing it. It's very interesting. So anyway, bye.